Hello, everyone. Thank you for being here today to listen to Blanca Fernández. She's a PhD student from the Physical Oceanography and Climate Group, and she will talk about the unfortunately famous marine heat waves.
Thank you, Paul, and thank you everyone for being here. I'm going to talk a bit about what I've done in my first 1.5 years of PhD. Some things I already presented, but I'm gonna go through them a bit quicker, so it's not the same all over again. First is why we study marine heat waves. Well, they, especially in the last few years, there's been a lot of talk about marine heat waves, and it makes sense because they have both ecological and societal impacts, and they can cost up to billions of dollars, and they can go all the way from impacts in species, in ecosystems, and also in economic activities like fisheries. I want to start with trends, with the temperature trends, because they are deeply linked to what marine heat waves are. Here is an example of the first things I did in my PhD, and there are simply SST trends in the Balearic Sea, and what it's obvious is that the temperature is increasing. And why I'm talking about this is because when we talk about streams, we always have to relate them to something. So mean in anything. Here we have a time series of this case is temperature anomaly. It could be anything, any variable, and we can see that there's an increasing trend. And if we separate it into two different time series, we have the distribution of the density probability distribution here, and we can see that they have different means and they are apart. And what does this mean? Is that if we compare the 90th percentile, so stream values of one over the other, if we're using this part to compute future extremes, we're gonna get that everything is under extreme conditions, like all these values that before, like if we use this part are not extreme conditions, if we are using this as a baseline to study all the time series, then they become extreme events. So the extreme events we detect are deeply linked with the shape of the distribution, both the mean and the variability we have. This in part is why some new research, or not new because it started around the 2023, that we're calling out on the most usually way we detect streams. That's using hot days and colleagues climatology, and it's always using SST satellite data because that's widely available. We have long time series and they cover most of the globe. And what they said is that, well, just take the first 30 years, at least 30 years. From that, you construct a climatology, a threshold, and every time temperature exceeds that threshold for at least 5 consecutive days, well, that's a marine heat wave. But what some people argue is that, okay, so if you always take those 30 years and temperatures are increasing, then we'll have more and more and more marine heat waves until everything is a marine heat wave. So here we have the temperature for the southwest of Mallorca in 2024, and we can see that with that first 30 years, in this case it goes from 1992 to 2011, all of the red part, that's a marine heat wave. But there are different methodologies that were proposed. So this is so in a way you can separate what impacts are due to the long-term warming of the sea and what impacts are due to the more like extreme events. Here we have an updating baseline. So instead of taking always the same 30 years to construct your climatology, you update it each year. And you can see that there's a decrease in the marine heat waves we perceive. And then another method that have been used is just to detrend the whole time series and do it over that detrend signal. So as it's expected, we only get an increase in marine heat waves. All these rows, they are different metrics that we use to describe or like to characterize marine heat waves. We have marine heat wave days, so how many days a year you have marine heat wave, the mean duration of those events, and then the mean intensity, the maximum intensity, and the cumulative intensity. And only with the fixed baseline, you get that trend, significant trend or increase in the metrics. Then we wanted to not really expand this, but using these methodologies, see what happened in the Mediterranean in 2024. And again, we start with a trend because, as I previously said, trend is really related to what we detect as marine heat waves. And here we have a particular thing that we didn't have as much in the Balearic Sea, that we have really different trends for different parts of the Mediterranean. So the eastern is warming more and more than the western Mediterranean. This is nothing new. Like more studies working with temperatures have described this. What we can see is that regardless of the method, so even if you use a fixed and moving a detrending method, 2024 had the most marine heat wave days and mean duration. So you can technically already like hypothesize that this is not due to the long-term increase, but to an international interannual variability. Then if we separate into two regions, so the western, as I said, with the lower trend, and the eastern with the higher trend, you can see first, as a general characteristics, the western Mediterranean tends to have more intense marine heat waves, and the eastern Mediterranean tends to have a higher number of marine heat wave days. But this is all related to that trend that we see in the eastern that is higher. And if we only look at the eastern Mediterranean, we see that what we expect is that if we reduce the impact of the trend, as a way to speak, because it's not really that, the perceived marine heat waves will really lower. For example, we can see here the difference between the yellow line and the purple line. But in 2024, even if we use different methods, it's still a year with really high marine heat wave days and mean duration. So this we use as to say that marine heat waves in the 2024 in the Eastern Mediterranean were really impactful. Well, not impactful, but were extraordinary compared to previous years. Then there are other studies that done this difference between trend versus variability when comparing marine heat wave days in different years. This, for example, is This, for example, is from a study by the Knights and colleagues, and it was published in 2025 on the what they did. Well, they say this is the trend, and this is the trend of the temperature, and this is the trend of the STD of the temperature. And what we can first see is that the distribution of the trends are really similar to ours, as expected. And also what they say is, well, if this relates to the change in mean values and the difference in the STD relates to the change in variability, in annual variability, then what they do is they do a thing that they call trend attribution ratio. Here, I just want to say, like, the only thing that's important is that the lighter values means that more of that metric can be attributed to the trend instead of the interannual variability. And we have different metrics, and they say that most metrics are driven by the trend, except for the mean intensity, which is a different. It can be explained by something different, and it mostly resembles what they say is the STD trend. And we see something similar too, because, for example, here we can see that the marine heat waves really increase with the trend, the method that that takes into account the trend, also mean duration, but mean intensity is not as clear. So that's one of the things that can cause different, really different values for the same year in marine heat waves. But what we saw during these two studies is that the trend, as I talked about it a lot before during this time, it really impacts on how we perceive them or how we calculate them. Here we have the two SSD trends maps I showed before, one for the Balearic Sea or for the whole Mediterranean. And before, between these two studies, it was only like less than 1 year apart. And using the same methodology and the same data set and everything, we can see that the trends are really different, like almost like a 20% difference in them. So what happened if we use the same methodology and the same trend and the same product? Well, the only thing that happened between these two products was a full reprocessing of the product. So even if it was the same data set, it had been preprocessed. So this can also change the amount of marine heat waves we see. And if you adapt to different methods, then you have to be really careful when you say a certain number, because there are a lot of sources of uncertainty that can go into that. Then, obviously, when you study the surface marine heat waves, it's really easy in a way because you have many data that you can collect with satellites, but in the end, it doesn't give you the full picture of information. All the impacts I mentioned, for example, the ecological or the fisheries, you wouldn't have them if you only looked at the surface. There has to be a change in the subsurface also to have those impacts. The problem with the subsurface is that it's difficult to maintain long-term time series, and also to have the spatial variability or the spatial coverage to get these studies to intercompare them. And also really important to build the climatology you need in order to complete anomalies to determine the marine heat waves. And we were really interested in how this subsurface marine heat waves were and how they related to the surface marine heat waves. So in 2025, using glider data, we sampled this transit repeatedly in order to try to answer these questions. This is a bit of the data description of the data we collected. It was this transit that it was going, we went over it 11 times over, I think it was 43 days. Each transect is 70 kilometers. And it was really nice because during this time, and with SST data, we saw that there was a really intense marine heat wave that happened in that same area. Here are a bit of the context of the surface during those days. This is just a quick plot. We can see that there's starting to some cold water starts to enter the area from the south, and that was really interesting because as we can see here, this is the temperature and the salinity, and we have it for the whole all the transects. I don't know if it's really visible, but there's red lines, vertical red lines that separate each transect. It's for the first two, how can I say? 400 meters and 60 meters. In the temperature, we can see an increase around the beginning of July, and that increase then later went into the whole water column. And in the salinity, we can see really a spot here or here of fresh or less salty water that also entered there. When we compare the surface versus the subsurface marine heat waves, we can see that this first increase in, sorry, this is the SST, and this is the whole data for the temperature. And we can see that this first increase in subsurface temperature is also visible in the surface temperature. And it remains relatively stratified until here, where you get mixing. And also this peak, you can also see it here. And then we have a second increase once the this surface layer has mixed, and it seems like this increase in temperature happens before this peak that we see here in SST data. And here is a bit of the TS plots per transect. So again, we see that in the beginning we have quite similar characteristics for all the transects, and that it gets warmer with time until more or less here that we start to see a split between the darker values that are the most offshore data and the lighter values that are the closer to the shore. And again, we have here this inclusion of fresh cold water that and also that here we have warmer water that then it gets a bit like mixing with the rest, so it's not as warm. These are some transects. The first one is the transect 1, that was when the glider was deployed, and we see again that all throughout the transect the data is quite homogeneous. And before this, before the glider was deployed, what we saw that it wasn't there anymore. It was that there was a cyclonic eddy that was leaving this area. And then here, transect 7, what you already can see this inclusion of colder waters and low salinity. And it's visible here in the temperature by this this structure that is going into the transect. And you can also see it in the SSH data. Here in transect 9, it's really clear the intrusion and also the shape of the structure. And honestly, there's still a lot to do with this data because we don't know if what I showed you before that there was an increase in subsurface data before the increase in subsurface temperature before the increase in SST. We don't know if that's primarily driven by both the first decrease and then the increase by atmospheric forcing or oceanic forcing. Also, we still don't know, but we have to look into how wind forcing influence the SST in that area, and how it also influenced the mixing. And further explore subsurface marine heat waves, because what I showed here, it wasn't truly a subsurface marine heat wave, but it was the subsurface expression of a marine heat wave. But in order to truly study what subsurface marine heat waves are, you need to first build that climatology to say that it was indeed a subsurface marine heat wave.
Any questions for Blanca?
I have, oh, good.
Very nice talk, Blanca. Thank you very much. You have improved a lot your work since last time I see you. It's very interesting what is happening underneath the surface. That is why we all see the satellite data. I have a question. Have you tried to explore other in situ data from before? Because it's really nice that you have a glider, but there must be available data, I imagine, in the Mediterranean, no? From floats or other stuff, so you can.
The problem is always the climatology. How do you get 30 years of daily or data in order to properly construct a climatology for each day of the year, so you can compare your values to that? Argo data, I know there is, but and there's available climatologies, but they are usually 1 month, so you cannot study events that are shorter than 1 month, like as magnetic waves. And this was honestly the first data we looked at, and we are interested also because there's SOFIP has the canals endurance line, which we have years data since 2011, and there would be a really nice data set to actually construct to try to see with that you can construct the climatology. But that's next step.
Oh, great. Thank you.
Yeah, so it's just that there was a slide in which you showed how you partitioned the Mediterranean Sea into east and west, and I was just curious about, so what is it that drives, so is there a principal way to say, okay, here is where I draw the line to east and west?
This one was mostly because of the, at first we did in 3 parts. Let me see if I find it.
I think it was 13 or something. Yeah, exactly that.
Here, yes. At first we did it in 3 parts, especially because maybe not here from here. We did it just through the Sicily Strait. And we did it in the eastern, central, and western part. But the thing is, with the central, you get this Adriatic Sea that is quite warm, quite high, not as high, but high warming trend. And then this Sicily, well, this, how do you say, Ionian Sea? That is has a really low warming trend. So in the end, it didn't make much sense to do it at 3. Also, we also thought about doing it through where you can see actually a division between the warming trend. I think we ended up doing this division because of previous studies that were also doing that. So in order to compare our trends to other studies, it was easier to just pursue that.
And well, at least do these other studies provide some rationale for doing that, for saying that that is the boundary somehow, that is what studies is. Maybe
I think the Western Mediterranean is more clear, that division, because more or less it has more similar behavior to what I consider the Eastern Mediterranean. But honestly, it was just to not work with that many, because I also did it by basic, like really small subbasins, but to not work with that many comparisons, so it was an easier thing. Also, this was for the Ocean State report, which is a really short. It's like a report that they do each year, and it requires a quite short word limit and only like 3 figures. So we thought that it was easier to tell the story and more submissions.
Okay, but then perhaps a natural curiosity is that, so once you decide to do a different partition, so this could be a way of kind of test the robustness of your results, right? So if you say, okay, if instead of cutting over there, I don't know, I partition it, I don't know, let's say all the way down through Italy, let's say, I mean, a completely vertical cut. And then I move it slightly then and see whether the results are still there or not. All right, and I'm just curious, so if somehow, so how important would it be for the results that you adopt a specific spatial subdivision as opposed to a different one? And so I would say that I'm not sure, but I would guess that there might be different ways of partitioning that. And then, so doing so might help in testing the robustness of the results if you really wanna compare two different things. I'm just asking, out of ignorance, to be honest, in the sense that I really don't know how one would like do that in principle, but.
Also, if, going back to what I showed with the Eastern Mediterranean and Western Mediterranean, here, this is what we saw here. As I said, this was mostly due to the trend. So, so the fact that 2024 is a lot higher is just because the Milky Way happened to happen there. But maybe if we, sorry, I lost what I was going to say. Yeah, what I say is that if we take a smaller part, probably this one, it will just get like more exaggerated because the Milky Way in 2024 happened to happen exactly there.
Mhm.
So you're right that the results will depend a lot of the area we take. But then this is just because we're doing time series of special average, but you can also show them in a map shape, like in a map plot.
Mm.
So if you just see how many, I don't know, the trends, but for each pixel, then that also gives you extra information. And I think we have that, but I just didn't see that.
If I understand correctly, you're saying that most of what is going on in the eastern part is driven by dynamics happening like so much east that basically it doesn't matter much how you draw the line between east and west.
It's just specifically for the 2024 that
Okay.
it happened here, and it coincides with the area that has the stronger trend. So it just gets.
Thanks.
But it's true that it would be really interesting to see how this sensitivity to the.
But so I was not coming from some kind of adversarial perspective. I was just generally curious about making this specific choice. If it is somewhat arbitrary, then one would ask, okay, if I just assume this is arbitrary and then I slightly move it around and I shift the boundary, and I wanna ideally see that the result is still robust. Thanks.
And it shouldn't be that hard to get this average difference.
The glider mission you had, is it something that is planned to be repeated this year or next year, or is it was only last year?
We're going to try to, well, it's planned to also do it this year, starting in the same day, so we can compare for the same, I think it's a bit longer, and see, so to also check the internal variability. Obviously, with 2 years, you cannot see much, but just to compare what happens. Please.
Very nice talk, thank you. I saw your observation has some limitation to the spatial coverage. And also you have glider, so on, so on. We give you one translate. If you have a numerical model, how to do to better study your marine Heatwaves, do you have any idea? Because we have a WMO model, which has high resolution, 2 kilometers. And now we are assimilating SWA data in there. So with the ADs and some fine scale structures, we can see very clearly. And I wonder if we make it longer, can we also study or help you to study on these marine Heatwaves? I
Obviously was only talking about in situ. So actually there are many studies done with modeling data, and actually also I have talked with Batis. So the things that what he said is that the model really captures well the variability of the temperature, so that's really useful when you want to construct the climatology. So you can see, like, I think the key thing is that what is difficult for in situ observation is that you don't have a climatology to compare against. And in that regard, that's where the models are really useful in this kind of study. So yes, they're definitely really great tools and really useful even using in situ.
Do you think modeling can help you to figure out the causes of marine heat waves or not move them? So
The causes, it will depend. If it's only modeling, I think even if you are, especially if you are assimilating in situ data, then maybe they're not totally physical coherent, no? So you're forcing them to have a result. So you cannot truly see the drivers. But if they are pre-run, you cannot compare, like cannot compare directly to what you see in situ, but you in situ similar situations, you can see what caused that marine heat wave. If that answers the questions.
So in our model, when we assimilate the in situ data in there, it's not only the model learns some information from in situ data, but also those data change the model physics in there. So there are two processes. One is directly correct the model by vertical projection of all the in situ data. The other way is through the physical adjustment of the model. And also.
So in the case of physical adjustment, we've seen it resolves well with kind of behavior and structures. Yes, I think it will really be helpful.
Okay, depends on the question.
Okay.